Hello everyone. We will try to explain some information which is beyond your lab manuals. We have learned how to measure the acceleration due to gravity using a simple pendulum in our school days. That we'll discuss what is a simple pendulum, how a compound pendulum and Ketter's pendulums is different from a simple pendulum, and above all, how to find G. So before going to the discussion, we'll have a short motivation why measuring G at a particular place is important. We know the value of G 9.81. It varies from 9.76 to 9.83, and the average value is 9.81. So we have Newton's laws of gravitation. If we have a earth that is having mass of me and we have a body mass m, then the force of attraction between these two bodies is g me into m by r square, and that is also equal to mg. So your acceleration due to gravity is g equal to capital G me by r square. This capital G is universal gravitational constant. This you all know. The value of this is 6.67 10 to the power minus 11 Newton into meter square per kg square. Now what is the motivation to find G? Before going to this, we will understand what is the structure of the earth. Based on the structure and the geometry of the earth and what is on the surface of the earth, G varies from places to places. So earth is actually a oblate spheroid, or you can imagine a oblate ellipsoid. That means it is offset from a spherical surface. So it is bulge at the equator and it is flattened at the poles. So our average value is 6371 kilometer. Near the equator, this value is more about 7 kilometer, and at the poles it is less about 14 kilometer. So because of this shape, this gm by r square formula, at the earth surface this g will be gm by r square. So this r is not a constant quantity. R varies from here to here to here and wherever you go. So g varies itself depending on the earth surface due to its structure. There are some other parameters, like earth surface is not uniform everywhere. Let's say this is earth surface, there could be some mountains, there can be sea, there can be trenches below the earth surface. So these are some height and these are some depth. So if you measure G here and G on the surface, it will not be the same. So G depends on height as well as depth. So these are the formula which you have studied in your class 11 in gravitation chapter. And G also depends on the latitude, which varies from places to places. So because of the rotation of the earth, we will have a angular velocity omega. We know we have a time period of 24 hours, so we can calculate the omega. So due to the rotation of the earth, this factor comes omega square r. And due to the latitude nothing but the angle between the equatorial line and at a particular place. If you draw the line to connecting to the place to the center, then you will find a angle lambda. So if you go to the pole, then your lambda is 90 degree. If you go to equator, then it will be lambda equal to 0 degree. So at poles, G at the poles will be G maximum and G at the equator will be G minimum, that is G minus omega square r. So these are the few factors which G depends on. So this is nothing new and this is well known to the scientists, and we have a standard database that wherever we go on earth, how G can varies depending on the height and depending on the depth and depending on the latitude of that particular position. Then why G is important? Is there any other factor that G depends on? So if you look at the formula that G is Gm by r square, and on the earth surface your small r is equal to the radius of the earth. So we can write Gm by r square. So if we consider that rho average is the average density of the earth, then m equal to 4/3 pi r cube into rho a. assuming that earth is a sphere for our simplicity of calculation. So if you just plug in this value here, you will get G is proportional to rho A. That means G solely depends on the density of the earth crust material. So here, wherever density is high below the earth crust, whatever materials are there, then your G will be high. And wherever this density is low, then your acceleration due to gravity will be low. So rho A, that is the average density, is not same everywhere, as due to internal structure of the earth. Let's say we have a rocky like structure. Below the earth surface there are layer of rocks. Then your rho will be high. And let's say below the earth surface there is sand, and below the sand there is some water bodies. So effectively the density rho 2 will be less than this rho 1. So rho 1 is greater than rho 2. So if I measure G at this particular position and G at particular this position, then your G1 will be greater than G2 due to the higher density. So actually in a field survey, whereby you want to dig on the earth surface, you must know what are those materials that is below the earth surface. Is it a rocky type surface, or is there any water bodies? So there we initially find value of G at that particular place. If that value of G is low than the actual value, that is, let's say it is less than 9.81, that means below the earth surface there is underlying some material that could have lower density. Like the metro work is going on, so before digging up we must do a G survey of that area, so that we can have a roughly estimation of the materials below the earth crust surface. So this was the main interest to find the G. So accordingly scientists wanted to develop some method what is the value of G. So initially there was pendulum, that is the simple pendulum. What is that? So simple pendulum is nothing but a bob connected in a string. So if you displace the pendulum from the vertical position at some particular angle, then it will oscillate in the mean equilibrium position. So in the simple pendulum, this length from the point of suspension to the point of oscillation, this length is L. Okay. So this length is length of the string plus the length of the diameter of the bob. But measuring this length L, there was an approximation. Approximation is that this string first of all must be massless. So the string will be massless. The bob which is connected, this bob must be a point mass. But in nature there is nothing like a point mass. Point mass means dimension is very low and the mass is very high. So this can only be happen if we increase the length of the string and the mass is so small, then we can assume that this is a point mass. So this is an approximation. So in the simple pendulum, the formula was G equal to 2 pi root over L by G. So this was the time period. So then we can find G is equal to 4 pi square L by T. So if you measure precisely L and if you measure the time period, then you can find the G. But as in the case of simple pendulum, there is approximation in the measurement of L itself. So we must arrive some method which can eliminate this difficulty. So there comes a method like compound pendulum. So this is a structure of simple pendulum that I have drawn. So in the deriving this formula, we have an approximation that the bob mass should be a point mass, that the bob will be a point like object. But in practical scenario, that we cannot form. So this is an assumption. So if we can increase the length of the string, this length, and R is so small so that it is very less compared to the length L, then we can call in this situation that the mass is a point mass. So this is a theoretical situation. practically it is not possible to achieve that condition, but we can have some approximation to calculate L. So what are others method that we can find using find G, and we can avoid this scenario of having a concept of point mass. So we have compound pendulum and we have Cater's pendulum. So in the simple pendulum, biggest sources of error that I am repeatedly saying that measuring L. So in simple pendulum it is simple pendulum, so it is not so simple to measure L because this is approximation. Also the string used must be inextensible, so there is error in measuring L itself. So alternative ways are compound pendulum and Cater's pendulum. So to begin with, let us understand the theory first for compound pendulum and Cater's pendulum. Then we can compare what is the advantage of compound pendulum over a simple pendulum, or what is the advantage of Cater's pendulum over a simple pendulum, or which one is better, a Cater's pendulum or a compound pendulum, to find G. So let's say this is a compound pendulum. So compound pendulum is nothing but any rigid body which can rotate about an horizontal axis. Let's say this is a body. We have a point of suspension here S, and we have a point of oscillation O here, and we have a center of gravity G at this particular point. So S is the point of suspension, G is the center of gravity, and O is the center of oscillation. Now if the body is rotated through some small angle, then due to the moment of inertia of the body, so if I displace the body from this position to this position at some particular angle theta, so it will execute a simple harmonic oscillation. We will try to derive the equation of motion and find what is the time period in case of a simple pendulum. So for a rigid body, if there is a torque due to the moment of inertia, then torque is simply I into alpha. Alpha is the angular acceleration, and torque is also defined as the moment of force. So I alpha is nothing but force mg into distance minus mgl sin theta. We put a negative sign here because the force is towards the equilibrium position, so we act in a opposite to the angular acceleration, so there is a negative sign. So for smaller oscillation, smaller angle, the sin theta can be approximated as theta. So this equation I alpha is equal to minus mgl sin minus mgl theta. Now if mk square is the moment of inertia of the body about G, let's say about this point the moment of inertia is mk square, then we can find the moment of inertia of the body about A as well using the parallel axis theorem. Let's say this is the axis, we know the moment of inertia mk square, then we want to find the moment of inertia about this axis I. So this is nothing but mk square, moment of inertia due to G, plus mass into distance between these two parallel axes ml square. So your moment of inertia is I equal to m into k square plus L square. So let us now rewrite this equation. So I can put alpha equal to mg L by I, theta equal to 0. Then alpha is nothing but second derivative of theta d theta by dt2 plus mg L by I into theta. So can you imagine the type of this equation? So this is nothing but a equation of simple harmonic motion like d theta d theta 2 plus omega square theta equal to 0. So if you compare these two equations, is omega square is nothing but mgl by I. So now we can find the time period t equal to 2 pi by omega. So 2 pi root over I by mgl. So if I just plug in I from this equation, so this is mk square plus a square, then mgl, so mm will be cancelled out. So this is k square plus L square divided by L times 1 by G. So we can simplify, so it is 2 pi root over k square by L square divided by G. So now if I compare this equation with the time period equation of the simple pendulum, 2 pi root over L by G, then your L is nothing but this k square plus L square. So let us rewrite. So L is k square plus L plus L. So this is the equivalent length for a simple pendulum. And we can exactly find out this value of L without any approximation like the simple pendulum. Let's say if we measure a length GO, okay, so look at this graph. So this is your GO, this distance. So this distance is nothing but k square by L along SG line. Then O is called the center of oscillation. The point S and O are interchangeable. That is, we can oscillate the body about this point, and we can invert the body and we can oscillate the body about this point O. So these S and O are interchangeable. That is, time period is the same whether the body oscillates about S or it is about O. Now we can rewrite this equation L square, L equal to K square divided by L plus L. So you can achieve this equation. Now let's say there are two lengths, L1 and L2 are the two values of this L. So we can have capital L equal to L1 plus L2 of this solution of this equation, and L1 and L2 equal to K square. So from the solution of this equation we can find L, the effective length of a simple pendulum from the compound pendulum graph, and L1 L2 equal to K square. So we can find K is equal to root over L1 plus L2. Now as you know that we have plotted the graph. So we have a bird-like pendulum. We put the oscillation point here and we got a time period far away from the center, that is this point. Then as you go from the point of suspension, you far deeper and more close to G, you will achieve this point. For this point you will achieve this point, and so on. As you go near the center of the gravity, this point, you will have time period higher. So you can see your time period varies with the length. It is because your length is varying according to this formula, and the relation of T and L is like this. So depending on the L, your T will be decided. So the graph is like a parabolic nature. Okay. So if you plot the graph both sides, if you invert the pendulum, let's say this is initially point of suspension, this is point of oscillation. Now if you invert the pendulum, this is now your point of suspension and this is your point of oscillation. So then you will get another graph like this. Now if I draw a straight line at a particular time t, I can see this line has cut 4 particular position, and at this 4 particular position these time periods are same. That means from the center of gravity towards the point of suspension there are 2 distinguished points where the time period is same. Similarly, from the center of gravity to the lower region or the other point, there are other 2 points where the time period are same. So actually this length PA is your L1, and this length QA, this length is your L2. So if I can find value of PA and value of QA from the graph, then I can simply find L. So L is nothing but PR plus QS divided by 2. Then I can write PR as PQ plus QA plus AR. Then SQ is equal to QA plus AR plus RS. Okay. So segment wise we can write this. So now PQ plus QA is nothing but PA. And AR plus RS, this AR plus RS is nothing but AS. So this is your AS. This 2 term out of this and out of this. Now what is AR and QA? AR and QA, these are all equal. So we can write 2 into QA. And this PA and AS, this is also equal. Okay. So I can write 2 into PA. So this is 2 into PA and this is 2 into QA. So this is PA plus QA. So this is nothing but PA, this length L1 plus QA, this length L2. So from the graph I can find L. So I can find L precisely from the graph, and there is no approximation like the bob must be a point mass. In this case there is no concept of point mass because this is a rigid body and the mass is distributed over the length. So concept of point mass is neglected here and that can be omitted. So that difficulty to find L with approximation is not here. So that is the advantage of compound pendulum. So we can omit that error in measuring G. Now from this equation we can also find K. So what was K? K was nothing but root over of L1 L2. So we know L1 and L2, we can find K. So using compound pendulum, I can find G at a particular place and I can find the radius of gyration of that body, as well as I can find the moment of inertia of that body about a particular axis. So in this experiment actually a different hole, we are varying the effective length and we are varying the moment of inertia. As the moment of inertia is varying, as you can see, then your time period will also vary. So that is why the nature of the graph is like this. So I have also explained why the nature is like this. If you look at the formula for simple pendulum, T is equal to 2 pi root over L by G, then your L is proportional to T square. So this is nothing but a equation like y square equal to 4ax, that is the equation of parabola. So if I plot y, that is T along y axis and L along x axis, so this will be a parabola. So you can see this same pattern is like it. There is more point, we can find this parabola symmetry. Okay. So now we can define the compound pendulum. Compound pendulum is a rigid body of any shape and is free to turn about a horizontal axis. And most importantly, in a compound pendulum, unlike simple pendulum, the point of suspension and the point of oscillation are effectively at large distance. Like point of suspension here and point of oscillation is the bob. So the distance to satisfy this is a point mass, this distance must be very large, okay. But in compound pendulum it is like a bar or any body is any random shape. This is your G, this is your point of oscillation, this is your point of suspension. So there is a finite distance between the point of suspension and point of oscillation. So that is the particular difference, simple pendulum and compound pendulum. Now we can define the radius of gyration. So radius of gyration, it is defined as the distance from the axis at which the entire mass of the body can be assumed to be concentrated without changing its moment of inertia. Okay. So it is a unique point about which the moment of inertia is same. So mathematically K is written as moment root over moment of inertia divided by m square. As I equal to m k square, then K equal to root over I by m. So by changing the distance from point of suspension, we can vary the time period and we can draw the graph to find the radius of gyration, acceleration due to gravity at a particular place. Now we can measure Z more accurately as there is no approximation in determining L. As a simple pendulum assumes a point mass, which is an idealization and harder to achieve in real life. So that is the biggest advantage in compound pendulum. Also it has an advantage shorter and compact design. You can design a compound pendulum to be much shorter than a simple pendulum while still achieving the same time period, which is useful in limited space. Now uses of compound pendulum. Compound pendulum is used in clocks, machine, precision instruments, like that. So we have learned about the uses of compound pendulum. What is the advantage of simple pendulum and compound pendulum? The readiness and the compactness of the design. So it is easy to carry compound pendulum. There is no approximation involved in it. So we can find G at a particular location. Now let us discuss another type of pendulum which is known as the Ketter's pendulum. So in 1880, Henry Ketter, maybe I have forgot the year, maybe it is 1818 or 1880, please look for that. Henry Ketter developed this Ketter pendulum. Okay. So if we look at the formula, we will start from the formula from the compound pendulum. We had an equation like this, T equal to 2 pi root over L by G, and L was K square by L plus L. Okay. So we can rewrite as K square plus L square divided by L into G. Now let's say in Ketter's pendulum, we will invert the pendulum in two cases. So we can find length L1 for time period T1 and we can find length L2 for time period T2. So we can write T1 in terms of L1 and T2 in terms of L2. So squaring this equation we will get this value and squaring this equation we will get this. Now if you subtract this equation 1 from equation 2, then we can get this value. So this is 4 pi square by G will be this term. Then this term you can smartly rewrite like this. You do some homework, you can achieve from this step to this step. So this is the working formula of a Keter's pendulum, and this is not discussed in the manual due to the limitation and to become the theory not too lengthy, okay, not too clumsy. So this way you can understand how the formula for Keter's pendulum is derived. So this is 8 pi square divided by T1 square plus T2 square L1 plus L2, T1 square minus T2 square L1 minus L2. In a manual we have written L1 and L2 as H1 H2, so we can write this like this. Now to understand the advantage of Keter's pendulum, let us simplify the above equation. Let us imagine a situation when T1 is very close to T2. Then this term will actually vanish. So the remaining term will be like this. So with this simplified equation, H1 plus H2 on this equation is the distance between the two knife edges, that is this knife edge and this knife edge. This is the total distance, H1 plus H2. So this total distance does not depend on the position of the center of mass. Let's say you made some mistake in measuring the center of mass here instead of here or instead of here. So your H1 and H2 will vary, but the total value of H1 plus H2 will still remain the same. So if you can achieve the condition T1 equal to T2, then it is immaterial to find exactly the where is the center of gravity of the system or center of mass of the system. Okay. So this is a very easy, and this is also much easier than compound pendulum. And we can say Keter's pendulum is also a one type of compound pendulum, but it is also known as the invertible pendulum, because both way we can oscillate and we can find the time period of oscillation. Now what are the advantage of Keter's pendulum? So there is no approximation like point mass, so there is no difficulty in measuring L. So we can omit finding the measuring of value of L, and with T1 equal to T2, position of center of gravity is immaterial, because we have already discussed H1 is H2, H1 plus H2, this term is nothing but the distance between these two knife edges. So this is the most used pendulum to find G and most popular, because this is not so time taking compared to compound pendulum, and there is no approximation like simple pendulum, so this can give G more accurately. So we can achieve greater accuracy with a precise measurement of T1 and T2. If we can measure time period T1 and T2 in millisecond, in microsecond, or even in nanosecond, then your value of G will be more accurate. So the precision depends on how you finally measure the time period. And this pendulum is also easy to carry. You can go anywhere with the pendulum, and you can find a G survey over any particular surface of the earth. And this pendulum is more advantageous than a compound bar pendulum as well, as it takes less time to find G. You do not have to find so many time periods to find G and plot a graph from that values. Now a question can arise: why we use a wooden block and a metal mass in a Keter's pendulum? Why the mass are unequal? That is the question. So this is because to have a asymmetric mass distribution. Otherwise, if the masses are equal, that is the weight W1 and W2 are equal, then, and if the weight W, this W is in the middle exactly, and W1 W2 are equal, then your G will exactly lie on the center. In that case, your H1 is equal to H2. So H1 is equal to H2, and if we are precise enough, then T1 will be exactly equal to T2. Then this term T1 square minus T2 square and H1 minus H2 will be 0 by 0. So this will be undefined. So that is why deliberately we choose a asymmetric mass distribution, so that this term survives. So we need a finite value of H1 minus H2 to survive the second term. So that is why there will be a wooden mass and there will be a mass of metal. And remember, these two masses shape also should be same to have same air friction. So that is, if you oscillate the pendulum from this point, it will air drag here, and if you oscillate the pendulum from this point, it will have air drag here. So if this shape of these masses are not same, then these two scenario, they will have different air drag. So to minimize the air drag, or to have same air drag in both the cases, we will keep the shape of the mass same, like cylindrical structure in our case. Okay. Now we'll define center of mass and center of gravity of a system. Now the center of mass of a body is the point at which the entire mass of the body can be considered to be concentrated for the purpose of analyzing linear motion. So it depends only on the mass distribution of object, and it can lie inside or outside the physical body. So let's say we have a bar and the middle there is a center of mass. If you apply some force from the outside, then it will have a linear motion. So if you hit at the center of mass, it will have only a translation motion. But if you hit the particular object away from the center of mass, then it will have a rotational motion. So center of mass is a unique point where if you apply some external force, then it will execute a translational motion. So this is also a definition of center of mass. So mathematically it is summation over mi xi divided by mi. Let's say there are three bodies, m1, m2 and m3. And from the origin this is x1, this is x2 and this is x3. Then we can find the center of mass as m1 x1 plus m2 x2 plus m3 x3 divided by m1 plus m2 plus m3. So this we can rewrite as summation over mi xi divided by summation over mi. So if you closely look, center of mass does not depend on the gravity. But what is center of gravity? Center of gravity is the point at which the entire weight of the body acts regardless of the orientation of the body. So it is a unique point where the entire weight of the body is concentrated. Means the gravity is only pulling that particular point only. Let's say if we have a body like this and this is the center of gravity. Let's say the earth is only pulling this point so that all the mass, all the weight is concentrated here. So this is center of gravity. So center of mass is concentrated, center of gravity, weight is concentrated, and it depends on the gravity. So it depends on both mass distribution and as well as on the gravitational field. And in a uniform gravitational field, the center of gravity of a geometrical object coincides with the center of mass. This we will discuss. Let's say we have a sphere. The center of mass will be obviously the geometrical center, and also center of gravity will also be the geometrical center in this case if this sphere is placed in a uniform field of gravity. That means G is everywhere same. G is pulling this point at same force, pulling this point at same force, and pulling this point with same force. Then the center of gravity and center of mass will coincide. Now let's say there is a situation where G is varying over the surface. Let's say G in this region is more compared to these regions. So this part of the sphere, earth will attract more towards it. So your center of gravity will be shifted from the center of mass. So this is an example. If we have a non-uniform G, then your center of gravity can shift from the center of mass. So this situation will only occur when you imagine a large body, say of 100 km, lying over a place where G is varying, then center of mass and center of gravity will not coincide. Let's say we have a earth surface, we have a large body over it, and G at this place, and at this place are all over varying. So your center of gravity and center of mass will not coincide at the middle point. Depending on the value of G, it will shift. So center of gravity depends on the value of G. So another example is moon. Let's say center of mass is the geometric center of the moon. It will exactly in the center. So that will not change. But if we consider the earth's gravitational field, some parts of the moon is closer to the earth. Let's say we have moon here and we have earth here. So this part, it is very close to the earth. So earth will pull this part with more force than this part. This part will be pulled with lesser force. So this part will be comparatively heavier than this part. So your center of gravity will shift from the center towards this point. So this is also a situation where center of gravity shifts slightly towards the earth. So these are some examples where your center of mass and center of gravity will not coincide. So you just have to say that wherever we have a non-uniform gravitational field, the center of mass and center of gravity cannot coincide to each other. Next, we will discuss Young's modulus using bending beam method.